Many robotics algorithms such as control or collision detection can benefit from accurate and high bandwidth link velocity and acceleration. However, numerically differentiating the encoder signal is not a viable solution as the noise characteristics intensify after each differentiation. We have previously shown that we can estimate the manipulator link variables including link velocity and acceleration by fusing IMUs with the robot motor encoders. For this, we installed one IMU per manipulator link. The measurements are consequently fused in a nonlinear estimator with the following dynamics model. It is evident that this method is computationally cheap, easy to implement, and covers wide range of trajectories. Next, we consider how we can improve the accelerometer measurement quality by optimizing the signal-to-noise ratio. Signal-to-noise ratio is a metric for the strength of the measured signal relative to background noise. With higher SNRs, the measurements will be more reliable. There are in general two methods to improve the measurement signal-to-noise ratio. Either to increase the signal power or decrease the noise power. With constant noise power, increasing the signal amplitude will directly boost the signal power. According to the kinematical equations for rigid bodies, the accelerometer signal amplitude is affected by the sensor distance from the rotation axis. Therefore, by increasing this distance, the accelerometer signal-to-noise ratio improves. Moreover, in order to decrease the Gaussian noise power, a general method is to increase the number of independent measurement sources. The experiment results show the effectiveness of these methods for improving the accelerometer signal-to-noise ratio. In order to evaluate the link variables estimator, we have installed one IMU per manipulator link. Consequently, the robot follows two different trajectories, namely slow dynamics motion and full dynamics motion. In a slow dynamics motion, we compute the Cartesian kinematics based on the estimated link variables. We compare our method against numerical differentiation of the robot pose information, which is provided by the robot interface. Moreover, a high precision device is used as the ground truth for this trajectory. However, the limitation is that this device can only be used when the robot moves slowly. We repeat this experiment in 3 axes of the robot base frame. Real-time Cartesian velocity in the y-axis of the robot is estimated here. Compared to the numerical differentiation of the robot pose, our proposed method is more accurate. There are some discontinuities in the jerk trajectory which degrade the estimation results. Our method works best when there is little discontinuity in the reference trajectory. In full dynamics motion, the robot moves along an excitation trajectory which persistently excites all robot modes. These trajectories are normally used for robot inertial parameters estimation purposes, as they reveal robot dynamics. We mainly report the link velocity and acceleration estimations in this scenario. We compare our proposed estimator against the numerical differentiation of the motor encoders. Since the laser tracker cannot follow rapid motions, we cannot use it as the ground truth in this scenario. Therefore, we filter the numerical differentiation of the encoder with lag-free filtering techniques and use it as the ground truth signal. As mentioned earlier, our method is recursive from the first link to the last link. Therefore, the accumulative error of our proposed method is obvious in the last links in both figures. On the other hand, quantization errors are amplified with respect to the sampling time after each numerical differentiation. The numerical differentiation errors are therefore so large for the link acceleration values. In summary, numerical differentiation is a viable solution for obtaining the robot manipulator's link velocity. However, our proposed method is a better solution for estimating link accelerations.